Welcome to Universe Intelligence. Today, we embark on a thrilling journey into the heart of matter. We're diving into the quantum world to answer a question that has intrigued scientists for over a century. What does an electron look like? Here, particles behave like waves, and certainty gives way to probability. Our exploration will uncover groundbreaking discoveries and mind-boggling concepts that have shaped our understanding of the electron. Get ready to explore the history of the electron's discovery and delve into the perplexing theories that describe its behavior. Fasten your seatbelts, because we're about to launch into a universe far stranger and more fascinating than you ever imagined. Our story begins in the late 19th century, a time when scientists were grappling with the mysteries of electricity and magnetism. The invention of the cathode ray tube provided a crucial window into this unseen world. When a high voltage was applied, a mysterious glow emanated from the negative electrode, traveling towards the positive electrode. These cathode rays became the subject of intense scrutiny and debate. Were they waves or particles? Scientists conducted ingenious experiments, deflecting the rays with magnets and electric fields. The rays behaved like streams of negatively charged particles, much smaller than atoms. This marked a turning point in our understanding of matter. In 1897, British physicist J.J. Thomson conducted groundbreaking experiments that would forever change our view of the atom. Thomson meticulously measured the deflection of cathode rays in both electric and magnetic fields. By analyzing these deflections, he made a remarkable discovery. Thomson calculated the charge-to-mass ratio of the particles composing cathode rays. This ratio indicated that these particles were incredibly light compared to their charge. Thomson had discovered a fundamental building block of matter, a particle far smaller and lighter than any previously known. He called it the corpuscle, but it would soon become known as the electron. Thomson's discovery of the electron necessitated a new model of the atom. Atoms were electrically neutral, yet they contained negatively charged electrons. To account for this, Thomson proposed the Plum pudding model. He envisioned the atom as a positively charged sphere with negatively charged electrons embedded within it. While Thomson's model was a significant step forward, new discoveries soon forced physicists to revise their picture of the atom. The quest to understand the nature and arrangement of electrons within the atom was far from over. As the 20th century dawned, physics stood on the brink of a revolution. The discovery of the electron, along with phenomena like radioactivity and blackbody radiation, challenged classical physics. The Newtonian laws were inadequate to explain the strange behavior of the very small. Max Planck in 1900 proposed that energy could only exist in discrete packets or quanta. This revolutionary idea marked the birth of quantum mechanics. Albert Einstein in 1905 further solidified the quantum revolution with his explanation of the photoelectric effect. Einstein showed that light could behave like a stream of particles, now known as photons. The debate surrounding the nature of the electron intensified with the advent of quantum mechanics. Was it a particle or a wave? Experiments seemed to support both viewpoints. In 1924, French physicist Louis de Broglie proposed wave-particle duality. De Broglie suggested that all matter, including electrons, possessed both wave-like and particle-like properties. In 1927, Clinton Davison and Lester Germer confirmed this hypothesis by observing diffraction patterns in electrons. This wave-particle duality had profound implications for our understanding of the atom. Electrons could no longer be pictured as tiny planets orbiting a central nucleus. The wave-particle duality of the electron led to another startling realization: the impossibility of simultaneously knowing both the position and momentum of an electron with absolute precision. This fundamental limit, known as the Heisenberg uncertainty principle, was formulated by Werner Heisenberg in 1927. Heisenberg showed that the more precisely we try to determine an electron's position, the less certain we become about its momentum. This wasn't due to any shortcomings in our measuring instruments, but rather a fundamental property of the quantum world. The uncertainty principle shattered the deterministic view of classical physics. In the quantum realm, probability reigned supreme. The quest to understand the electron had led us to a profound shift in our understanding of the nature of reality itself. Our journey into the heart of the atom now takes us to the realm of electron orbits. Electrons don't follow precise paths, but exist in fuzzy clouds of probability called orbitals. These orbitals, defined by specific energy levels, dictate the electron's energy and its likelihood of being found in a particular region around the nucleus. The further an orbital is from the nucleus, the higher its energy level. Electrons seek stability by occupying the lowest available energy levels. This arrangement of electrons within energy levels gives an atom its unique chemical properties. The quantum dance becomes more intricate as we move to heavier atoms with more protons and electrons. Now let's focus on the outermost occupied energy level of an atom, known as the valence shell. This shell, and the electrons residing within it, called valence electrons, hold the key to an atom's chemical behavior. The driving force behind these interactions is the pursuit of stability, often achieved when the valence shell is full, typically containing 8 electrons. This is known as the octet rule, and it governs much of the chemical world. Noble gases like helium, neon, and argon are famously unreactive due to their full valence shells. For most other elements, the quest for a full valence shell drives them to form bonds with other atoms. This intricate dance of electrons gives rise to the incredible diversity of molecules that make up our universe. The desire for a full valence shell drives chemical bonding, the process by which atoms link together to form molecules. One common type of bond is the covalent bond, where atoms share electrons to achieve a stable octet. Imagine 2 hydrogen atoms, each with a single valence electron. Alone, they are incomplete, yearning for stability. But bring them close together, and their electron clouds overlap, forming a stable hydrogen molecule, H2. Carbon, with its 4 valence electrons, is a master at forming covalent bonds, creating a vast array of molecules. The world of molecular chemistry is a vibrant dance floor where atoms waltz and twirl, sharing electrons to form the molecules that make up our world. We've explored the concept of electron shells, those quantized energy levels that dictate how electrons are arranged around the nucleus. Each electron shell contains even finer subdivisions known as energy sublevels. These sublevels, each with their own unique energy and shape, provide a more detailed map of the electron's whereabouts within the atom. Think of it this way. If electron shells are like floors in a building, then sublevels are the individual apartments within each floor. These sublevels, designated S, P, D, and F, each with their own characteristic shape, dictate how electrons are distributed within a given shell. The shapes of these sublevels arise from the wave-like nature of electrons and the mathematical equations that govern their behavior. This subdivision of electron shells into sublevels is crucial for understanding the chemical behavior of elements. To navigate the intricate world of electron shells and sublevels, physicists use a set of 4 quantum numbers to pinpoint the location and energy of each electron within an atom. The first quantum number, the principal quantum number, indicates the electron's energy level or shell. The second quantum number, the azimuthal quantum number, defines the shape of the electron's orbital or sublevel. The third quantum number, the magnetic quantum number, describes the orientation of an electron's orbital in space. Finally, the spin quantum number describes the intrinsic angular momentum of an electron, its spin. These 4 quantum numbers provide a unique set of coordinates for each electron within an atom. No 2 electrons can have the same set of 4 quantum numbers, a principle known as the Pauli exclusion principle. The arrangement of electrons within these energy sublevels has profound implications for the way atoms interact with light. When atoms absorb energy, their electrons can jump to higher energy levels. But this excited state is unstable, and the electron quickly returns to its ground state, releasing the absorbed energy as a photon of light. Each element emits a characteristic set of wavelengths of light, known as its atomic spectrum. By analyzing the light emitted by distant stars and galaxies, astronomers can determine their chemical composition, temperature, and motion relative to Earth. The study of electron configurations and atomic spectra has unveiled a profound connection between the microscopic world of atoms and the vast expanse of the universe. From the colors of a sunset to the composition of stars, the behavior of electrons within atoms shapes the beauty and diversity of the cosmos. Atoms become positively charged ions, or cations, by losing electrons. The nucleus attracts electrons, while electrons repel each other. This balance determines ionization energy, the energy needed to remove an electron. Metals with low ionization energies lose electrons easily. Understanding ionization energy helps predict chemical behavior. Section 2. A Symphony of Spin. Unraveling the principle's origins. The Pauli exclusion principle might seem like an arbitrary rule, but its roots lie in the fascinating world of quantum mechanics, specifically in the concept of electron spin. Electrons, in addition to their orbital angular momentum, possess an intrinsic angular momentum, a sort of spinning motion, even though they are not literally spinning spheres. This spin, quantized and having only two possible values, spin up or spin down, plays a crucial role in determining how electrons can occupy atomic orbitals. The Pauli exclusion principle dictates that if two electrons share the same orbital, same n, l, and ml values, they must have opposite spins, one spin up and one spin down. This pairing of electrons with opposite spins within the same orbital minimizes their electrostatic repulsion, contributing to the stability of atoms. The exclusion principle, by dictating the spin states of electrons within orbitals, shapes the very architecture of atoms. Pauli's insight into the role of spin and his formulation of the exclusion principle earned him the 1945 Nobel Prize in Physics. His discovery not only revolutionized our understanding of atomic structure, but also paved the way for advances in fields like astrophysics, chemistry, and electronics. Section 3. From Exclusion to Stability, Shaping the Atomic World. The Pauli exclusion principle underpins the stability and diversity of the chemical world. It dictates the electronic configuration of atoms, determining their chemical behavior. Consider hydrogen with its single electron, and helium with its two electrons. The exclusion principle makes helium chemically inert. Each element adds one more proton and electron. The exclusion principle results in periodic trends in reactivity and atomic size. It governs electrons in molecules, solids, and stars, a fundamental principle woven into the fabric of the cosmos. Section 4. Antimatter and the positron, a mirror universe. Our journey into the heart of the electron has taken us from the dawn of the quantum revolution to the elegant dance of electrons within atoms. But our exploration wouldn't be complete without venturing into one of the most mind-boggling concepts in modern physics: antimatter. In 1928, British physicist Paul Dirac predicted a particle with the same mass as the electron, but opposite charge. This particle, the positron, was initially met with skepticism. In 1932, Carl Anderson observed the positron in cosmic rays. The positron's discovery confirmed Dirac's prediction and provided evidence for antimatter. Antimatter annihilates matter in a burst of energy, raising profound questions about the universe. Section 5. Farewell from Universe Intelligence. As we conclude our exploration of the electron, we're left with a sense of awe and wonder. This tiny particle, once a mysterious flicker in a cathode ray tube, has unlocked some of the most profound secrets of the universe. From its wave-particle duality to its role in chemical bonding, the electron has challenged our classical intuitions and forced us to embrace the strangeness of the quantum world. Its story is a testament to the power of human curiosity and our relentless pursuit of understanding the cosmos. Thank you for joining us on this journey into the heart of matter. If you enjoyed this exploration of the electron and the quantum world, don't forget to subscribe to Universe Intelligence and hit that notification bell so you don't miss out on our next cosmic adventure. And here's a little joke to leave you with. Why don't scientists trust atoms? Because they make up everything. Until next time, keep exploring the universe and never stop questioning the world around you.